Hello, everyone. Welcome to Physics 213. This is the General Physics 2 lab, and this is lab 0. And I thought I would start by reviewing a couple of things that we did last semester and will be important this semester as well. So what I want to do is review how to compute percent experimental accuracy and also percent experimental error. Remember, those are measures of precision and accuracy. And then I want to review vectors, in particular, how to add and subtract vectors. That'll be very important in a later lab when we look at electrostatics and when you look at this in lecture as well. Okay, so what I did was I started the first few pages of this handout where I went over a problem where I review how to compute percent experimental accuracy first. So I want you guys to look at that example carefully. Remember, again, percent experimental accuracy. It's also called the relative average absolute deviation. And really, it's a measure of precision, right? It's a measure of the variability in the data. Then I went over an example where I reviewed how to compute percent experimental error. Remember, that's when you compare an experimental value to an accepted predicted gold standard value. Okay, and then finally, I do a review of vector addition where I add two vectors together. Again, you guys can carefully go through this, where I'm adding basically two force vectors together. Okay, and then after that is the actual lab report itself. So these are going to be group lab reports as usual. And in this case, I just gave you a bunch of problems for this first lab, for this lab 0. Okay, and I'll talk about these in a little bit. So what I want to do is I want to review these things, but I don't want to do exactly the same examples I gave you. I want you to have some different examples. So let me go to the iPad and review how to compute these things. Okay, so let's start with percent experimental accuracy. And remember, this is also called the relative average absolute deviation. If you remember from last semester, percent experimental accuracy is not really a great name for this measure because it's really not a measure of accuracy. It's a measure of precision, right? It's a measure of the variability. However, we're kind of stuck with it because this is a name that is used throughout the lab manual, and the lab manual was written way back in the early 70s, 1970s, where this term was used. So we're kind of stuck with it. So just remember, accuracy is a measure of the variability. All right, so let me make up a problem here. Let's say I want to measure the length of some object 5 times. So the length in meter 5 times. And let's say this is my data. So I have length in meters. And let's say this is my data, 5.432 meters, then 5.437, 5.442, 5.438, and then 5.444. Okay, so 5 measurements, and I want to calculate the percent experimental accuracy, or I want to get a measure of the variability, right, of these 5 measurements. So remember, the first thing that you have to do is you have to average these 5 values. So how do we average these? Well, you simply add them up and divide by 5. So if you do that, right, you're going to find that you're going to get 5.4386. And then this was very, very important. Now we want to round our answer. So we want to round our average to the resolution of the instrument, which in this case, the resolution of this instrument is, since it's 3 decimal places, is 0.001, right? So the resolution in this particular example is 0.001 meters. So this has to round to 5.439 meters. So that's going to be the average, right? That's our average length. Okay, then remember the next step was to form a second column here of what's called the absolute deviations, right? So we had a second column of absolute deviations, also in meters in this case. And these represented how far each data value is away from your average, right? Away from your mean. So the way that you would compute that mathematically is you would take each data value, so 5.432, subtract your average, 5.439, and then take the absolute value of that. And if you do that, you're going to find in this case, you're going to get 0.007. Okay, so you do this for each case. I'll do all this out, but in general, you can basically do this usually in your head, right? Because you're just asking like, how far is this data value away from the mean? Well, it looks like it's 0.002 meters away, right? But if we do it out, then I would subtract, again, the mean from that particular data value, take the absolute value, I'm going to get 0.002. So again, I'm going to write everything out, but if you can do this in your head, that's fine too. So this one's going to be 0.003. Then 0.001. And then finally 0.005. Okay, next step. Remember, next what you do is you average the absolute deviations, right? So I add up all these absolute deviations. I divide by 5. I find the average. If you do that, you're going to get 0.0036. But again, we want to round to the resolution of the instrument. So we want to round to 3 decimal places. So this is going to be 0.004. Okay, and again, remember, this is called the average absolute deviation. So average absolute deviation. Okay, now we're almost done, right? So now to compute percent experimental accuracy, I take my average absolute deviation and I divide by my average value, in this case, my average length. And then to convert that ratio or that fraction to a percent, I multiply by 100, right? And then add a percent sign. So this is going to be 0.004 divided by 5.439 times 100. And if you work that out on your calculator, you should get 0.07%. So it's a very small number, which is good, right? Remember, the smaller the value here, right, the closer to 0, that means that there's very little variability. Okay. The other thing that you have to remember is that this average absolute deviation can never be less than the resolution of the instrument, right? If this happened to be 0 or something really, really small, you'd have to use at least 0.001 here. But in this case, it was greater than that, right? 0.004, so we could just use that value directly. Okay, so hopefully you remember that. It's important, again, in this semester, we will be calculating this quite often. Okay, the next thing I want to review is percent experimental error. This is sort of the easier one. So percent experimental error. So you compute this when you want to compare an experimental value to an accepted predicted gold standard value, right? So let's say we did an experiment and we found the experimental value for density, let's say we're measuring density, to be 3.21 grams per centimeters cubed, right? It was some metal, let's say. And then we found that the accepted value for density, remember, this is also called the predicted, I might use gold standard or even theoretical. Etc. Right? There were several ways of describing the accepted value. We often use predicted as well. So let's say we looked this up in a handbook or on Google, and we found that the accepted value, the predicted value for that density of the metal was 3.02 grams per centimeter cubed. So the question is, how do I compute the percent experimental error? Well, remember what you have to do. I'm running out of room here. Let me do this on the next page. So again, the experimental value was 3.21 grams per centimeters cubed, and the accepted or predicted was 3.02. Okay, so then if we wanted to compute the percent experimental error, then the formula was, remember, was the difference between the experimental value and the accepted. But we had to keep it positive, so we took absolute value of that. Then you divide by the accepted value. That's the important thing. That denominator always has to be the accepted or gold standard value. And then times 100 just makes that fraction a percent. So in this case, right, it would be 3.21 minus 3.02 absolute value divided by the accepted, which is 3.02 times 100. And if you work that out, this is going to be 0.19 divided by 3.02 times 100, which is around 6.3%. So in this case, the percent experimental error was 6.3%. Not great, but not too bad, right? Remember, the lower, the better. And for percent experimental error, we can get exactly 0%, right? If your experimental value was exactly the accepted value, the same as the accepted value, your percent experimental error would be 0%, and that's okay for error. Okay, again, hopefully that's review. This is something that we'll be computing, multiple times this semester as well. Okay, and then the big thing I want to review is dealing with vectors, adding vectors together, subtracting vectors, looking at vector components. Okay, so let's do this problem. where we add vectors together. And again, you can look at my handout for an additional example, right? Make sure you understand that one as well, but let's do a separate one right now. Let's say I have, so I'll just call this section adding vectors. All right, let's say I have a coordinate system. And I have vector A. So this is vector A. This is my XY coordinate system. And let's say A is at 28 degrees with respect to the positive x-axis, right? Remember, you measure counterclockwise. And let's say the magnitude of A, remember magnitude, I can either write like this. So it's like absolute value of the vector, or you could just write the letter itself, A. Let's say that's 44.0, whatever the units are. Let's say it's a lane. Let's say it's meters in this case. So this is meters. Okay. Some books actually use double vertical lines also to represent the length of it, the magnitude of it. It means like the norm of it. Okay. So all those really mean the same thing. They're the magnitude of that vector A. Then let's say I have vector B, which is like this. And let's say the angle it makes with the positive x counterclockwise is 124 degrees. And let's say the magnitude, I'll just write B here, is 26.5 meters. And then finally, vector C, let's say it's straight down. So this is vector C. And let's say its magnitude is 31.0 meters. If you want an angle here, and you measure from the positive x counterclockwise, and this angle would be 270, right? To get to go straight downward. So 270 degrees. Okay, so now what I want to do is I want to add those three vectors together. Let's start with that. So let's say we want to find I'll call it the resultant vector R, which is A plus B plus C. So I want to add those three vectors together. All right, so the way that we should start this is we should find the components of each vector, right? Find the x and y components of vector A, find the x and y components of vector B, find the x and y components of vector C, and then we know to get the resultant vector, we need to add those components together. Okay, you add all the x components together, you add all the y components together. All right, so let's start with A here. So what I'm going to do is I'm going to draw A just separately in a coordinate system. I know that its magnitude is 44.0 meters. I know this angle is 28 degrees. Right? Again, this is x, this is y. And I want to find the x, y component. So basically, if I project that vector onto the x-axis, so if I draw a perpendicular from the tip onto the x-axis, then this is going to be ax, right? That's the x component of A. And if I project a vector onto the y-axis, then this is going to be ay. So I want to find ax and ay. So what you can do here is you can extract the right triangle that contains the reference angle. In this case, the 28 degrees here is the reference angle. A reference angle is always the angle that the vector makes with the x-axis. It could be either with a positive x-axis or the negative x-axis, but it's with the x-axis. So this is the triangle, the right triangle I want to extract. Okay, so let me do that. So I know that this angle is 28 degrees. I know that the hypotenuse, right, is the magnitude of A. So that's going to be 44.0 meters. And then this is AX. And then this side is AY. Okay, so how do we find AX and AY? This is where our right triangle trigonometry comes in. So let's start with AX. Well, AX is adjacent, right? It's next to this angle. It's adjacent to the angle here. And this is the hypotenuse. So then we have to ask ourselves, what trig function relates the adjacent side to the hypotenuse? And remember, that's going to be cosine, right? SOHCAHTOA, sine is opposite over hypotenuse. Cosine would be adjacent over hypotenuse. So in this case, we know that cosine of 28 degrees must be the length of the adjacent side, which is AX, divided by the hypotenuse, which is 44.0. And then I can solve this for AX, right? I can multiply both sides by 44. I'm basically multiplying by the lowest common denominator to clear out the denominators. Right, so these cancel. And then finally, I'm going to get AX is equal to 44.0 times cosine of 28 degrees. And that turns out to be 38.85 meters. Okay, do the same thing. And actually, it's positive, right? To get the sign, whenever you use a reference angle, you have to make sure you have the correct sign for the components. But because I know that AX is pointing to the right here, I know it's going to be positive, right? So it's going to be positive 38.85. And AY is also going to be positive because it's pointing up. Okay, so let's do AY now. So AY is opposite the angle. So I know that the trig function that's going to relate those is sine. So sine of 28 degrees is equal to AY divided by 44.0. So that means AY is going to be 44.0 times sine of 28 degrees. And if you work that out, that's going to be 20.66 meters. Okay, and that's also positive, right? Because it's pointing up. So now our vector A, if you want to write, hopefully you guys remember, I think that this was mentioned in lecture, but one way of writing the vector is in terms of the unit vectors. So remember, I hat is a unit vector in the x direction. And then j hat is a unit vector. Unit vector just means it has length 1. Unit vector in the y direction. So any vector can be written in terms of the unit vector. So in this case, right, we would write A, vector A, as the x component of A times I hat plus the y component of A times j hat. So I could write this as A is equal to 38.85 I hat plus 20.66 j hat. And really it has units, right, of meters. So that's vector A. Okay, so we found A in terms of its components. Let's do the same thing for B. Let me go back up to the top here. So now for vector B, it was in the second quadrant, right? So it was something like this. We know its magnitude was 26.5 meters. And we knew this angle was 124 degrees, right? 124 degrees. Okay, so we want to find the x and y components, right? So we want to find bx. So if I project this onto the x-axis, this is going to be my bx, which we can tell is negative, right? Because it's going to the left. And if I project my vector onto the y-axis, this is going to be my y component of b, by. So what I would do first is you could use the actual angle of 124 degrees, and it will come out right on your calculator with the correct signs. But I think it's easier to think about this always by using the reference angle. Remember, the reference angle is the angle that the vector makes with the x-axis, either positive or negative x-axis. So in this case, it's just going to be the angle that the vector makes with the x-axis right here, with the negative x-axis. How do we find that angle? Well, that angle is going to be 180 minus 124. Right? So in this case, it would be 56 degrees. Why do I do it this way? Because then we can think about always extracting a right triangle, and then we don't have to worry about signs. We can get the signs correct later just by looking at the directions of the components, bx and by. So I'm going to extract out that right triangle, right? So this triangle right here is the one I want, that one that contains the reference angle. Okay, so now that it's a triangle, right, a right triangle, then the signs don't matter. We can figure that out later. We know the hypotenuse again, that's going to be the magnitude of B, so that's 26.5. And I'm looking for BX and BY. So to get BX, again, since it's adjacent, I can use cosine. So cosine of 56 must equal BX over 26.5. Therefore, BX is going to be 26.5 times cosine of 56 degrees. So that's the magnitude, but then to get the correct sign, since we know that BX is pointing towards the left, then it's going to be negative, right? So this is really going to be negative. And if you work that out, it turns out it's negative 14.82 meters. And then to get the y component, I use sine, right? Sine of 56 is going to be by over 26.5. So therefore, by is going to be 26.5 times sine of 56 degrees. And that's positive, right? Because it's pointing up. So this turns out to be 21.97 meters. So vector B itself, let me write it down here next to A. I can write as negative 14.82 I plus 21.97 J. And again, it has units of meters. Right, so I found the x and y components of B, and I just wrote it in terms of the unit vectors. I think it's easier just writing everything in terms of unit vectors. Okay, and then the last one we have to look at is C. But C is actually the easiest one, right? Because, draw this out here. So this is x, this is y. Remember, C is going straight down. It has a magnitude of 31.0. If you want, you could use this angle and plug in sine and cosine, but you don't have to. You can just think about this, right? The x component of C is 0, right? Because none of that vector is projected into the x direction. And the y component, well, it's all in the y direction and it's negative. So the y component must be negative 31.0 meters. So vector C, if you write it in terms of our unit vectors, I hat and j hat, this is going to be 0 I hat minus 31.0, all right, 0, j hat meters. Okay, now that we found the components for each of our vectors, now we can add them together, right? So go to a new page here. So remember, our resultant vector, which is what we want, is going to be the sum of vector A plus vector B plus vector C. So resultant is going to be A. Well, we know A, I'll write it in terms of the unit vectors, is 38.0 20.85 I hat plus 20.66 j hat plus b, which is negative 14.82 I hat plus 21.97 j hat plus c, which was 0 I hat minus 31.0 j hat. So how do we add these? Well, remember, we just add the components. So basically, I'm going to add the i's together and then add the j's together. Right? So my resultant is going to be, I'll do it this way. So just going to do the i's, 38.85 minus 14.82 plus 0. That's I hat. And then I'll do the j's. So 20.66 plus 21.97 minus 31.00. And this is j hat. So then that leads to, if you do this out on your calculator, you're going to find that this is 24.03 I hat and then plus 11.63 j hat. So that's our resultant vector, right? That's our sum of those three vectors in terms of its components. Okay, if you don't like using the unit vectors I hat and j hat, another way that you could do it, and I sometimes do it this way, is by making a table. Let me just show you this. You know, whatever way you find easier, you should use. So I sometimes just make a table, right? So I have vector A, vector B, vector C, and the x components and y components I know, right? I know that the x component for vector A was 38.85. These are really meters. Y component was 20.66. For B, the x component was negative 14.82. And then the y component was 21.97. For C, the x component was 0. And the y component was negative 31.00. So I'm just going to add them together, which means add down the columns. It's the same exact thing. It's just another way of organizing our work here. So to get our resultant vector, if I want our x, I add down this first column here, right? So I add these values together. And of course, when you do that, you're going to get 24.03. And if I add down the y's, I'm going to get the y component of my resultant, which is 11.63. Again, these are meters. Okay. Now, ultimately, so we have our resultant vector and it's in terms of its components, right? Ultimately, what we might want to do is we might want to find the magnitude and direction of that resultant vector. So what I do now is I usually draw out the resultant vector. So it has an x component of 24.03, right? So let's say that is right here. So this is Rx, 24.03. And then Ry is positive 11, so it's going to go up. So Ry is 11.63. Again, these are meters. So my actual vector R is this vector, right? That goes from the origin to here. That's got to be R. And it has a particular angle, call it phi. So I want to find the magnitude of R, which is the length, right, of R, and then I want to find the angle. So remember the magnitude, if you want, you can think of this as a right triangle, right? So I can extract out this right triangle now. I'm looking for the magnitude, let's call it R, and this angle theta. And I know that this length is 24.03 and this length is 11.63. So to find the magnitude, you simply use Pythagorean theorem, right? So that R, in general, it's going to be the square root of Rx squared plus Ry squared. So in this case, it'll be the square root of 24.03 squared plus 11.63 squared. And if you work that out, it turns out it's going to be 26, I'll round it to one decimal place, 26.7. 26.7 meters. Okay, now to get the angle theta. Well, again, if we know the adjacent side and we know the opposite side, what trig function relates adjacent and opposite? Tangent, right? Tan is opposite over adjacent. So I know that tangent of, I'll call it, in this case, I guess I use phi for my angle. So tangent of phi is going to be opposite, which is 11.63 over adjacent, which is 24.03. But I don't want tan of phi, I actually want phi. So now remember, to get that, I have to do the inverse function of both sides. So the inverse tangent of phi gives me phi, right? It gives me that angle phi. Remember that an inverse function undoes the original function and gives you back the argument. So really, I mean, usually you never even write that, but really we're doing inverse tangent of tan phi to give us phi by itself. And then the right-hand side, inverse tangent of 11.63 over 24.03, that ratio, you have to plug that into your calculator and you should get 25.8 degrees. So that's my answer. So R has a magnitude of 26.7 meters, and it has a direction of 25.8 degrees above the positive x-axis, right? Counterclockwise in the positive x-axis. Okay, great. Hopefully that was mostly review. Let's do one more thing. Let's find the difference between vector A and vector B. So I want to find vector A minus vector B. Let me give that a name. Let me call it W. So W is going to be A minus B. Okay, so the question is, how do we subtract vectors? Well, it's just like subtracting numbers. You can think of subtraction as being the same as adding the opposite, right? So this I could rewrite as vector A, that stays the same. And then I want to add, since we already know how to add vectors, I want to add the opposite, which is negative B. So vector A minus vector B is the same as vector A plus negative vector B. So how do we find negative vector B? Well, first of all, let me write down B again. So B, remember, was, let me go back here. I guess it was negative 14.82 I plus 21.97 J. Okay, so negative B really means like -1 times B. And how do we multiply a vector by a scalar, by just a number, -1? You just multiply each component by that value, right? So this is really going to be -1 times -14.82 I plus 21.97 J. So if I distribute in that -1, it's just basically going to change the sign, right? It's going to be positive 14.82 I minus 21.97 J. Okay, so that's negative B. So now if I want to find A minus B, well, that's the same as A plus negative B. So I know what And remember, I called this W, right? W is going to be A minus B. So A we already know, right? A was 38.85. I hat plus 20.66 J hat. And I want to add negative B, so this is going to be positive 14.82 I hat minus 21.97 J hat. So I add the i's together, just like before, right? I add the i's together, and then I add just the j's together to get my resultant, which I'm calling W here. So W now is going to be 38.85 plus 14.82 I hat. And then for the y component, I have to add the j. So this is 20.66 minus 21.97 j hat. So W is going to be, it looks like 53.67 I hat, and it's going to be a very small j hat, right? In fact, negative, I guess, 1.31 j hat. Okay, so that's the answer. That's A minus B, which I'm calling W, in component form. Now, if we want it in magnitude direction form, we can do that, right? So again, I would draw this out. So vector W looks like this, right? It looks like WX is 53.67, and then WY is negative 1.31. So it looks like W is going to be in the fourth quadrant, or vector, or A minus B vector is going to be in the fourth quadrant. So it's going to look like this. And this is our angle. Let's call it phi again. So that's W. So how do I find the magnitude and the direction? Well, again, let me extract out this right triangle. You always extract out the right triangle that contains the reference angle. Remember, the reference angle is the angle that the vector makes with either the positive x-axis or the negative x-axis, right? It's with the x-axis. So I'm just going to extract out that right triangle. So this is phi. This is, now the negative and positives don't even matter because these are just lengths now, right? It's a triangle, and this length is 1.31. Okay, so how do I find the magnitude of vector W, which I'm calling W? Pythagorean theorem, right? So W is going to be the square root of 53.67 squared plus, and again, you could use WY as negative, but it doesn't matter because you're going to square it. So it's 1.31 squared. And this turns out to be 53.69 meters. And now I also want to find the angle phi. So I know that tan of phi is going to be opposite divided by adjacent, right? Relative to this angle phi, this is the opposite side, this is the adjacent side, so TOA. So that means phi, if I take the inverse tan of both sides, I get phi is equal to the inverse tan of 1.31 over 53.67. And that turns out to be, it's a very small angle, right? Around 1.4 degrees. So I could either say that my angle is 1.4 degrees south of east, right? Or you could say you could say below the positive x-axis. That's one way of describing it. If you actually want this angle that starts at the positive x and goes counterclockwise, and we call it theta, we could find that, right? So theta in this case would be 360 minus 1.4. And that would be 358.7 degrees. So you could either use phi by itself, 1.4, but then you have to say like, south of east. You have to give some more information so that we know that we're in the fourth quadrant. Or if you just give an angle directly, then it's implied that you're starting at the positive x and measuring counterclockwise to the vector. Okay, so this would be the magnitude of vector w, and this would be the direction, 358.6 degrees, or 1.4 degrees south of east. All right, great. So let me go back to the handout and describe what you guys need to do for your lab report. So again, review the few examples I did here as well. I just wanted to give you some different examples. You have... Okay, so for the lab report. So the first question is basically computing percent experimental accuracy. So I give you this problem. It says the diameter of a basketball is measured 10 times with a caliper, which has a resolution of 0.01 centimeters. Using the data below, compute the average diameter of the basketball and the percent experimental accuracy for the diameter. Okay, so find the average diameter. Then of course, once you remember, round it to 2 decimal places, right? Then you have to find all the absolute deviations. You average those, round to 2 places, and then you can compute the percent experimental accuracy. Okay, then I go on and say the volume of a sphere is, the formula is 4/3 pi r cubed. Since the diameter of a sphere is twice the radius, so diameter is 2 times r, we can rewrite this formula for the volume of a sphere in terms of diameter. And so if I plug in for r, if I plug in d over 2, then I can simplify this to be 1/6 pi times diameter cubed. So assuming that the basketball is a perfect sphere, I want you to compute the volume of that basketball, given what you found for the average diameter here. So you're just plugging into this equation. And then also find the percent experimental accuracy for the volume. Now remember, how do we do that? Well, if I know the percent experimental accuracy for the diameter, and the formula involves multiplying diameter by itself 3 times because it's diameter cubed, then remember, to find the percent experimental accuracy for the volume for this dependent variable, you have to add the respective percent accuracies. So basically, and the 1/6 and pi don't have any arrows, so you don't have to worry about that. It's just the diameter here. So since it's diameter cubed, which is diameter times diameter times diameter, then to find the percent experimental accuracy for volume, you're going to take your percent experimental accuracy for diameter here, and you're going to add it together 3 times, right? Or just multiply by 3 is the same way of saying that. And that will be your percent experimental accuracy for the volume. Okay, then suppose that the accepted value for the volume of a regulation basketball is 7,130 centimeters cubed. You have your experimental value, right? You just computed it here. This is your volume here. So I just want you to find the percent experimental error. Compare your value, your experimental value, with the gold standard, with the accepted value. Okay, so that basically was, the 2 problems that involve percent experimental accuracy and percent experimental error. The next problems involve vectors. So problem 2. It says charge Q2 and Q1 each exert a force on charge Q3. And I drew a picture of it in this figure here. If the force on Q3 due to Q1 is 140 newtons, so we're looking at the forces on Q3, right? So Q1 exerts a force on Q3 in this direction. You guys will learn more about this. Because this is a negative charge, this is a positive charge. Unlike charges attract, so this charge is going to exert a force in this charge in this direction. So think of this as the force on 3 due to 1. So this 3, 1 here means on 3 due to charge 1. Okay, you don't have to know anything about force, about charges and Coulomb's law. We'll learn that when we talk about electrostatics. All you have to know is that the force is in this direction, and we know the magnitude is 140 newtons. Okay, then charge Q2, so Q2 exerts a force on charge 3, Q3, in this direction. They're like charges, so they repel. So I have, this is the force on 3 again, right? On 3 by 2. And we know the direction is straight up, and we know the magnitude, it's 325 newtons. So all I want you to do is find the net force acting on charge 3 here. So basically, I want you to add F31 and F32, add those two forces together. So you're going to have to like create a coordinate system. You should have enough information here to figure out the angle, so you can figure out the components of each force, and then you add the components together. Okay, and then represent it. I want ultimately the answer to be in terms of a magnitude and a direction. Okay, so that's problem 1. Or actually it's problem 2, I guess, in the set. Problem 3 is another vector, our second vector problem. It says a ball collides with a wall with a velocity of 100 meters per second at an angle of 40 degrees with respect to the wall. So here's the incoming ball, right? So here's the velocity. So this magnitude is 100 meters per second, and the angle here is 40 degrees. It rebounds off of the wall, and it's an elastic collision. So it comes off also at 100 meters per second and at 40 degrees. So this is V2. So what I want you to find is the change in the velocity of the ball. Remember, change in velocity is the final, like V2 minus V1. So how do we subtract vectors? Well, we can write this as a vector addition, right? I can write this as the change in velocity is V2 plus negative V1. Okay, so we just did an example like that with subtraction. So you want to kind of follow the same idea. And you should find, right, you can even think about this in terms of, if this is V1 in this direction, right, we know that negative V1 will be the same length in the opposite direction. So it would point like this. So if I have V2 plus negative V1, we can add it graphically, like tip the tail. If I take negative V1 and I put the tail at the tip of V2, it's going to go something like this. So we know our answer has got to be like along the positive x-axis. It's got to be in this direction. Okay. All right, problem 4. So 4 forces are acting on a central ring. So I'll show you the figure in a second. You're told the magnitude of each force, and you're given the direction in the picture here of each force. So here's F1, it acts at 45 degrees above the positive x-axis, and you're given the magnitude in the problem. F2 is 180 degrees, so it's acting exactly along the negative x-axis. F3 is 70 degrees below the negative x-axis, and F4 is 30 degrees below the positive x-axis. So what I want you to do is add those 4 forces together. So find the net force, which is F1 plus F2 plus F3 plus F4. And again, give your answer as a magnitude and a direction. Okay, then the last problem, I kind of had fun making up this problem here. This kind of like tests all your knowledge of like geometry, trig, vectors. So you're told that you have a 15-foot by 12-foot room that needs to be cleaned, right? It needs to be vacuumed. You have a robot vacuum cleaner. Think of it as like a Roomba. Okay, it starts in the southwest side of the room, as shown in the diagram. I'll show you in a second. And you're also told the diameter of the vacuum cleaner is 1.2 feet, which means the radius is 0.6 feet. Okay, a Cartesian coordinate system is attached. At the start, the center of the robotic vacuum is at the origin of the coordinate system. So it's at the coordinate 0, 0. The robot starts by moving at an average speed of 45.72 centimeters per second at an angle of 20 degrees with respect to the positive x-axis until it encounters the east wall. Okay, so let me look at the picture right now, show you this. So here's a robot vacuum cleaner, right? It's starting, here's the coordinate system, I hat, j hat, right? X, Y. And think of this center as being at 0, 0. So it rotates 20 degrees and it moves in this direction, right? At an angle 20 degrees. So this is like the displacement, the first displacement, until the edge of it hits the wall, right? So now the center right here, well, first of all, you know it's going to be like 0.6 feet away from the wall, right, the center when it hits, because we're just tracking the motion of the center of this robot. So then what it does is it rotates 114 degrees counterclockwise, so like this, and then it's going to travel in this direction until it hits a piece of furniture. So there's a piece of furniture here. Okay, so let's say so it encounters the east wall. It then rotates 114 degrees counterclockwise and then travels at an average speed. It's always traveling at the same average speed of 45.72 centimeters a second for 3.5 seconds until it hits a piece of furniture. The robot then rotates 136 degrees counterclockwise and travels at an average speed of, same thing, 45.72 centimeters a second until it encounters the south wall. So once it does that, right, it's going to rotate again, and it's going to basically be somewhat downward, right, until it hits the south wall. And then finally, it rotates a certain degrees clockwise until it ends up here. And I kind of, to help you out, I kind of gave you what the final position should be, something like this. Okay, so it'll be a good check to make sure that you're doing this problem correctly. So it encounters the south wall, and then finally, the robot rotates 150 degrees clockwise and travels at an average speed of 45.72 centimeters a second for 6 seconds until it comes to a complete stop. And again, I drew exactly where it should be stopped, so you can check yourselves to make sure that you're doing everything correctly. Okay, so then I broke the problem up into steps. So the first step is we want to solve this problem in US or English units, right, in feet per second. So you need to convert, first of all, the speed, the average robotic speed, from centimeters per second to feet per second. So do that first, right? Convert from centimeters per second to feet per second. Okay, second question. In the diagram below, I have drawn the individual displacements D1 and D2. So I started the process for you, as well as the net displacement, which is going to be the sum of all of your 4 displacements, D1 plus D2 plus D3 plus D4. The displacement refers to the change in position of the center of the robotic cleaner. Using a protractor and ruler, sketch D3 and D4 on the diagram. And a good thing, so this should be exact. If you, when you print this out, when you print out this picture on your printer, it's a PDF, make sure that you choose the option actual size. Then the scale factor will be exactly 1 centimeter is 1 foot. Okay, and you can check this because remember the room should be a 15-foot room. So this length here should measure 15 centimeters if you're printed out correctly. And then it'll make it easier when you're measuring these things with a protractor and ruler. So I've done D1 and D2 for you. You want to finish up D3 and then D4, right, to get D net. Okay, then part C, for each part of the path, find the individual displacement of a robotic cleaner. So find D1, D2, D3, D4. These quantities should be found analytically and presented in component form, right? So like D1 is going to be the X component of D1 I hat plus the Y component of D1 J hat. D2 will be the X component of D2 times I hat plus the Y component of D2 J hat and so on. Find the width of the piece of furniture. So again, using the information, everything you learned, you should be able to figure out what this width is in terms of feet. Okay, it'll be a nice, easy value. I'll give you a hint on that. Find the net displacement. So now that you have all these displacements, the individual displacements, D1, D2, D3, and D4, you can add them all together, and that will be your net displacement, right? Found in component form. And then you also want to find this net displacement in terms of the magnitude and direction. So if you know it in component form, if you know the X and Y components of the net displacement, then you can easily find the magnitude and direction. Okay, check your analytical answer by measuring the length of the net displacement with a ruler, right, in centimeters, and measure its angle with a protractor. And then you should find that there's going to be some error, right, with the protractor getting it exactly, but you should find they're very close, right? In theory, they should be equal. And then the last part here is Given that the average speed of the robotic vacuum cleaner was 45.72 centimeters per second for each part of the path, and assuming that it took no time, let's assume that it took no time for the vacuum cleaner to rotate when it changed direction, what was the average velocity of the robotic vacuum cleaner? And the hint here is, remember, average velocity has a magnitude and a direction, right? It also depends on the direction. And remember, average velocity is defined to be the displacement, so like the net displacement divided by the time. Okay, so really the average velocity should be in the same direction as this net displacement. Okay, but really I want you guys to think a little bit about this question. So, okay, and then that's it. And then one person from your group, all right, remember you're going to form lab groups again, typically of 3 students, but you could have up to 4 students, or a minimum of, or yeah, I'd say a minimum of 2 students, a maximum of 4 students. One person from your lab group will submit this lab report, lab 0, on Brightspace, and then I'll grade it and get it back to that person, and then you can distribute the grades to your lab partners. Okay, hopefully this will be a helpful review. Again, when we need to use vectors in the future in this course. Great, thank you.